This matrix element, and in principle also all those matrix elements eventually will end up with this kind of 2 electron integrals. And those are 2 electron integrals over molecular orbitals. Do you all understand that notation? That's sort of called the physics notation. Let's write that up. The main topic is integral transformation. Well, let's first write up what an integral, which is I, J, A, B. What is that? I mean, this is an integral, and we call it a 2 electron integral. So it's obviously an integral over the coordinates of 2 electrons. So let it write as a double integral, but in reality it's not a double integral, it's a... How many variables do we actually have in a 2 electron integral?
Two volume elements. But
2 volume elements, right.
Yeah.
So in principle we have, I mean, if I write it sort of with the position vectors of both electrons, so this is 3, that is 3, that's actually a 6th tuple integral. But you could write it with 2, normally people don't do it, just write an integral sign. And that's sort of the volume element then. Now, that's sort of really, you can translate that really to the normal notation. So that is electron 1, so you have a molecular orbital phi of, depending on electron 1, complex conjugate. Then you have another molecular orbital, J, and it's also complex conjugate. That's of electron 2, and now I need more space. Then in the middle, that bar is sort of meant to represent the operator, which in atomic units is just the distance between the 2 electrons. And then we have, again, phi A, that's electron 1, and we have phi B, electron 2, and then the 2 volume elements, like this. So that's what this means. There's also a notation with round parentheses, where you sort of have interchanged those 2. In the round parentheses, you sort of have the idea that in the first part you have electron 1, in the second part you have electron 2. You sort of have the density of electron 1 and the density of electron 2, which then would be I, A, and then J, B. That's the chemist notation, if you see that in, and I think in the literature people are actually, at least theoreticians are reasonably consistent. This notation is definitely. So this is sort of electron 1, and that would be electron 2, and then the first one always is the one which is complex conjugate. Right, back to whatever notation we use, these are molecular orbitals. And obviously in order to solve the Hartree-Fock equations, we had to calculate all those 2 electron integrals in the original atomic orbital basis set, because that's what goes into the Fock matrix. So we might have those integrals around, same kind of integrals, but now let's see, what kind of letters do I use? Greek ones, yeah, because the Greeks came before the Romans. So Greek are natural indices for basis functions. We had integrals, same type, but over our basis functions. CCP VDZ, and you get a lot of those integrals, and you need to calculate them in order to solve the Hartree-Fock equations. Let's assume we calculate them and we have them still lying around, right in a big file on the hard disk. So we have those around, but now we need those. Those are the molecular orbital bases. These are molecular orbitals. And here we have basis functions. Now what is between them, of course, we know each molecular orbital is a linear combination of all the basis functions times the coefficient. So if let's write that for a second here. Remember, each molecular orbital, phi, for example, phi I, is a linear combination of all the basis function with this kind of molecular orbital. And these are the molecular orbital coefficients. MO coefficient, which are the eigenvectors of the Fock matrix. That's what comes out of the Hartree-Fock calculation. And in order to get those, that's the main reason for doing the Hartree-Fock calculation. I mean, normally you're not really interested in those orbital energies. You're interested in those coefficients because you need them in order to make the molecular orbitals. So in principle, not in principle, but in practice now, I can insert that expansion for all those 4 molecular orbitals. And that means I get actually 4 summations. The first one runs over alpha, beta, gamma, delta. And then each of them is a more basis function times the coefficient. And let's see, I see, what do I call it, alpha I, but that was complex conjugate, so that coefficient should be complex conjugate. If we would allow non-real wave function, which we normally don't do, but anyway, let's write it. Then this is J, yeah, complex conjugate, C, gamma A, C, delta B. So before we can calculate those matrix elements, or any other, I mean, it doesn't have to be A, B, it can be I, J, K, L, or Q, R, S in general. You have to do that. And that's called the integral transformation, or 2-electron integral transformation. And that might be the part when you sort of, while the calculation is running, you're looking at your output file, you can see that the Hartree-Fock calculation is finished, and the program doesn't write anything to the output file any longer. For seconds, hours, or days, depending on how large the molecule is, and you're wondering what the hell is the program doing, it might be doing that. The 2-electron integral transformation. Now if you look at that, you can see, I mean, obviously I have 4 summations here, and each summation runs over all basis functions. So if I have n basis functions, capital N basis functions, that process is going to be n to the 4th power. But you have to do that for each I, J, A, and B, but that's actually n to the 8th power operations you have to do. I mean, each time you have to do sort of a multiply. And actually it's sort of 1, 2, 3, 4 multiplies. So if you want to count how many operations you have to do in order to do that, if you would do it straightforward like this, it's 4 times n to the 8th power multiplication. That's going to take some time. Until someone figured out that this is a real stupid way of doing it. And you can do that smarter by doing things one at a time. If you split that up in 4 steps, so if you can start with with just doing the first summation, delta C delta with B, for example, chi A, chi beta, chi gamma, chi delta, and you get a kind of intermediate where you have. And do you mind if I drop the chi's? Just write alpha, beta, gamma. Alpha, beta, gamma, delta. And remember, the Greeks came from the Romans, so the Greek letters are basis functions, the Romans are molecular orbitals. So this would be then alpha, beta, gamma, B. That's sort of intermediate. You calculate that first, and then you take the next one. C gamma A, I think I call it. And you have this one, alpha, beta, gamma, B. We get sort of the next intermediate, alpha, beta, and then you have A, B, and you do that twice more. Then you actually end up with having a process which is 4 times only n to the 5th operations. So by making these kind of intermediates, you save a lot of time. So that's one of the technical, practical issue when you want to do correlated wave function calculation, that you have to get the integrals into the molecular orbital basis. You can sort of do that on the fly. You could either have the integrals written on disk because you use them for RTFOC, or you recalculate them whenever you need them. But you still have to transform it to the molecular orbitals, because all correlated wave function methods are obviously in the basis of the molecular orbitals, and not in the original atomic basis function basis.